Okay, so today we're going to finish the last section of Chapter 9 talking about percent yield. So first, let's kind of review a little bit of what we talked about so far. First section, we talked about mole ratio. So this mole ratio is using the balanced chemical equation to convert between compounds. Okay, then we incorporated that along the balanced chemical equation to convert from grams of one compound to grams of another, and then we related that to limiting reactants. And so the limiting reactant is basically the reactant that controls the amount of product being produced. And so it's the one that produces the least amount of product. And so that's how we figure that out. When this reactant is used up, the products will stop forming, and so we call it the limiting reactant. So let's do a little bit of vocab, since we're going to talk about percent yield. Well, if you think about percent is like your grade. Okay, so it's your points over the total. And so we have two different kinds of yield. The first one is theoretical yield. So remember, if you yield something, it's the amount of product produced. So theoretical yield is the amount of product that's predicted from the amounts of reactants used. So we're assuming that the reactant converts completely to product, all the limiting reactant is used up. We're assuming a perfect world situation. So this is the calculated yield. So it's theoretical. We're assuming it's going to work out perfectly, so this is what we get from calculations. The other type of yield is actual yield. This is the amount of product that's actually obtained, and this has to be experimentally determined. So we're going to do a lab where you're converting, for some of you, I believe it's copper to silver, and so you can determine the theoretical yield through calculations, and then the actual yield by actually massing out the product that's left, and then we can calculate the percent yield. Percent yield kind of gives an indication of how efficient the reaction is. If your percent yield's really high, it means your reaction was really good. It was really efficient. Okay, and so percent yield compares actual to theoretical yield. So the equation, and you can write it if you don't want to write all the words, so percent yield equals actual yield over theoretical yield times 100. So it's kind of like your points divided by the total points times 100. Okay, so let's look at a couple examples. So we've got our equation, or chemical reaction, and we know that 68.5 grams of carbon monoxide reacts with 8.60 grams of hydrogen gas. So we want to calculate the theoretical yield of CH3OH, which is our product. And in order to do that, we need to find the limiting reactant. And then the second part of this problem is if 35.7 grams of CH3OH is actually produced, we want to find the percent yield of methanol. Okay, well, let's write our reaction, and we're going to have to flip back and forth a little bit because I'm not going to remember anything. Okay, so we've got carbon monoxide plus hydrogen gas goes to CH3OH. Okay, I remember that part. 68.5 grams and 8.6 grams. So we have 68.5 grams and 8.6 grams. Whoops, wrong way. Okay, and we want to calculate theoretical yield first. So let's do that. Okay, let's just write everything down because we're going to have to come back anyway. So 35.7 grams of CH3OH. All right. So that's how much is actually obtained. So actual yield is 35 point, oh, dang, what was it? 7, I swear. Can't remember anything. Okay, so this is how much is experimentally or actually produced. So if we want to find percent yield, and we also want to find theoretical yield, well, we're going to need theoretical yield first, and then we can put the actual and the theoretical yield together to get percent yield. Well, if we want to know how much is theoretically produced, we need to find our limiting reactant. So that's our first step. So let's take our grams of carbon monoxide, so 68.5 grams of carbon monoxide. We're going to need to go all the way to grams of CH3OH, or at least moles, so we can compare. So we're going to need to use the grams to moles, so molar mass of carbon monoxide, then mole ratio, and then molar mass of CH3OH. So again, since this is kind of review, if you want, go ahead and pause the video, do this on your own, and then just fast forward to the answer and see if you get it right. And then you don't have to listen to me. Alright, so we want to calculate the molar mass of carbon monoxide. Well, carbon's about 12, oxygen is 16, so it's about 28. grams. Okay, so that gives us moles. Now, of course, I forget, and I always forget to do this, we need to balance our equation so we can do the correct mole ratio. So let's take a look. Carbon looks okay, oxygen looks okay, but we have 4 hydrogens on the product side and only 2 on the reactant side. So I'll put a 2 up front, and otherwise we should be balanced. So now for every 1 mole of carbon monoxide present, there's 1 mole of CH3OH produced. And now let's go to grams. So for every 1 mole of CH3OH, we need the molar mass. So let's see, we had carbon and oxygen, so that was 12 plus 16, so about 28, and another 4. This should give us about 32. Okay, so now let's just calculate. So we're going to take our 68.5 divided by 28 times 1 divided by 1, not going to do anything, times 32, and we get 78.28 grams CH3OH. So what this means is if carbon monoxide was completely used up, theoretically we would produce 78.28 grams of CH3OH. So now let's see what happens if the hydrogen gas is our limiting reactant. So we're going to start with 8.6 grams of H2. And let's see, that's about 2 grams in 1 mole. And then we need our mole ratio. So for every 2 moles of H2, there's 1 mole of CH3OH. And then we need the molar mass for CH3OH. We already did that. So for every 1 mole of CH3OH, there are 32 grams. So let's calculate this one. 8.6 divided by 2 divided by 2 again, times 32, 68.8. Okay, so what this means is if all the hydrogen gas is used up, we will produce 68.8 grams of CH3OH. So since this is the smaller quantity that makes H2 gas the limiting reactant, this will never happen because we'll stop at the 68.8 grams and we'll never go past that. So our carbon monoxide then is the excess reactant. Okay, so this is the first part, and let's see, I see 2 significant figures, so technically this is 69 grams of CH3OH, although I think I probably forgot the 0, but we'll go with what we have written down. Okay, so that is the theoretical yield. So now if we want percent yield, that's actual yield over theoretical yield times 100. So our actual yield was 35.7 grams. Our theoretical yield was our 69 grams. Multiply by 100, or you can just move the decimal 2 spots. It's really the same thing. So 35.7 divided by 69 times 100. So 51.7% yield. If we're going with our 2 significant figures, 52%. So not the most efficient reaction, because only 52% of what we put in is what we got out as product. So, okay, so you may have to determine the limiting reactant first to decide how much product is theoretically going to be produced, and then given actual yield from the experiment, so it would have to be given, you can find percent yield. So let's try one where we need to find actual yield given percent yield. So here's our reaction. We have 6.71 times 10 to the third grams of TiCl4, so we'll put that one underneath. Whoops, what'd I do? There we go. And we've got 2.45 times 10 to the third grams of O2, and only 2.12 times 10 to the third grams of TiO2 is obtained. That's the actual yield. Okay, so if the percent yield is 75, so let's write that down underneath also, we want to know the theoretical yield. So we're solving for theoretical yield. Now there's a couple ways that we could do this. Because we know both the reactants, we could find the limiting reactant, and that would in turn give us the theoretical yield. Or because we know percent yield and actual yield, we can just solve it that way as well. So what you could do is try it both ways. It'd be good practice for the limiting reactant part, and then you could just compare. Okay, but we know that percent yield is equal to actual yield over theoretical yield times 100. So if I was going to rearrange this equation, first thing I do is get rid of the 100. So I'm going to divide it since it's already being multiplied. And then let's see, I need theoretical yield, so I want to get that out of the bottom, so I'm going to multiply on both sides. And then let's see, I'll multiply back by the 100, probably didn't need to move that in the first place, and then divide by percent yield. So I should end up with theoretical yield is actual yield times 100 divided by percent yield. So if I plug in, actual yield is 2.12 times 10 to the third grams times 100 over my 75%. I can write 75 because my 100 is in here. If you want to take the 100 out and just move the decimal, then you'd have to write 0.75. Okay, so let's solve this. So 2.12 times 10 to the third times 100 divided by 75, 2,826.7. And that's grams of TiO2. Significant figure-wise, it looks like we're at, I guess we would probably go with 2 here. So 2,800 grams. You could also write it in scientific notation. Keep in mind that the theoretical yield should always be bigger than the actual yield. If it's not, then something happened. There's no way to get more mass than what is theoretically determined. So if you do end up with a larger actual yield, then go back and check your calculations. All right, so try some practice, and if you have any questions, we'll go over it. Have a good day.